This is an interesting concept in waves. It's called the Doppler Effect. And you may have experienced this with sound waves, but this is actually true for all types of waves. And we'll get into some other times when you would see this Doppler Effect. An easy kind of way to picture the Doppler Effect would be the siren of an emergency vehicle. So you might have noticed that as an emergency vehicle is approaching towards you, the sound of the siren appears different than the sound that you hear when it's moving away from you. This is essentially caused by the difference in the apparent frequency that you are hearing the sound. This is similar to the breaking the air or the sound barrier question we saw with aircraft, where the faster an aircraft is moving, it could possibly start to move faster than the sound it's producing. So if it's moving towards the sound it's producing, we have this compression of the sound waves in front and a rarefaction of the sound waves behind. But the Doppler effect isn't necessarily necessitated on the moving of the source. It could also be occurred due to the moving of the receiver. It's named after Christian Doppler, who was an Austrian physicist and mathematician who first analyzed the phenomena. However, not all moving sources of sound will generate a Doppler effect. For example, the speed of the moving source must be a reasonable fraction of the speed of sound. So about 10%. So if the speed of sound is 330 meters per second, then you'd have to have an emergency vehicle moving at about 100 kilometers per hour in order for that to be heard. In addition, the moving source of sound has to have a component of its velocity vector moving parallel to the detector. That's the person or the source that is, or the not the sound source, but the receiver of the sound. Here's what you can copy down for the Doppler effect. When V is constant, so as a sound approaches, we appear to have a lowering of the wavelength and an increase in the frequency. And as you move away, we have an increase in the wavelength and a decrease of the apparent frequency. Now, I was saying this happens with all types of waves, and it actually happens with light waves as well. If a galaxy or a star is moving away from us on Earth, the observers, we would actually have a shift in the light, and when this happens, we have two types of effect. We either have a shift towards red light, which is called a red shift, or we have a shift towards blue light, which is called blue shifting. Short-range radar devices, such as those used by police, also work on the Doppler shift principle to determine the speed of a car. So what would happen is the police car speed radar measuring device would send out a radar signal, and it would basically detect the change in the frequency or the wavelength that would be expected, and using that it can determine the speed of the car. State what happens to the apparent frequency of a sound source in each of the following situations. So if we have a stationary listener with a sound source that's approaching, in this case we would have sound waves compressing, and because those sound waves are compressing, that means that the wavelength appears to be shorter. We have a greater frequency. The listener is stationary and the source is receding. So here the source is receding, so the wavelength appears to be larger, which means we have lower apparent frequency. If we have a stationary source and a listener approaching, here the listener approaching, and we have to assume this is at a decent speed, so this would be about 10% of the speed of sound at the time. We have compression of the sound waves as the appearance of the listener, so there would be an increase in frequency, decrease in wavelength. And the last situation, if our source is stationary and the listener is receding, it's the opposite, where we have an apparent increase in the wavelength, so we have a decrease in the frequency.